Our telescope in the Canary Islands released an image that's currently breaking every quiet conversation in astronomy labs around the world. A comet, or something calling itself a comet, hurtling through our solar system with a tail 6,000 kilometers long. But here's the problem. The tail points toward the sun, not away from it, as every comet in recorded history has done. Toward it. Imagine water running uphill. Imagine smoke falling instead of rising. That's what astronomers woke up to yesterday morning. A violation so clean, so absolute, that the first reaction wasn't excitement. It was disbelief. The object is called 3I Atlas. The 3I means it's the third confirmed interstellar visitor we've ever tracked. It came from somewhere beyond our solar system, unannounced, moving at speeds that don't match anything gravitationally bound to our sun. And right now, as it swings past our star, it's behaving like nothing we've seen before. This isn't just an anomaly. It's a constellation of anomalies. A jet aimed the wrong way. A chemical signature that defies every model of planetary formation. A pulse, rhythmic, mechanical, repeating, every 4 hours. Something built, not born. If this sounds impossible, that's because it is. According to physics, at least. Before we dive in, I need you to do something. If you're watching this because you want answers that don't insult your intelligence, if you want to follow this investigation wherever it leads, even if it gets uncomfortable, hit like, subscribe, and let me know in the comments where you're watching from. Because what we're about to explore isn't just another space mystery. It might be the moment we stop pretending we're alone. Let's begin. When a comet forgets the rules, the photograph is clean, almost too clean. Captured by the tidy 2-meter telescope in the Canary Islands, processed through standard Laplace filtering to enhance faint structures, the image shows a bright nucleus, the head of the comet, surrounded by a glowing cloud of gas and dust. Standard fare for any comet passing near the sun, except for one thing. Extending from the nucleus, stretching 6,000 kilometers into space, is a narrow jet of material. Thin, focused, unmistakable, and it's pointing directly toward the sun. Let me be clear about why this matters. Comets are dirty snowballs, frozen water, carbon dioxide, methane, ammonia, all locked together in a loose gravitational embrace. When a comet approaches the sun, heat does what heat always does. It melts ice, it boils volatiles, it turns solid into gas. That gas expands outward, carrying dust with it, forming the tail we see from Earth. But here's the thing. Radiation pressure from the sun pushes that tail away from the star. Always. It's not optional. The sun's light exerts physical force on particles, shoving them outward like wind filling a sail. Every comet tail in history points away from the sun, no matter which direction the comet is moving. It's one of the most reliable rules in the solar system. Until yesterday, the jet on 3I Atlas is angled at roughly 280 degrees from the sun-comet line. In plain language, it's pointing into the solar wind. It's moving toward the source of pressure that should be pushing it back. Water running uphill. Astronomers noticed immediately. Within hours of the image's release, observation requests flooded into every major observatory with line of sight to the object. Hubble Space Telescope, the Very Large Telescope in Chile, JWST, still the most sensitive infrared eye humanity has ever built, was tasked to swing its mirrors toward this tiny, fast-moving speck. Because if the jet is real, if it's not some artifact of image processing or atmospheric distortion, then we're looking at one of two things. Either the physics of cometary outgassing is fundamentally broken, or this object isn't following the physics of comets at all. The first option rewrites textbooks. The second option rewrites everything. Let's talk about what interstellar means. 3I Atlas was first detected on March 8, 2024 by the Atlas Survey, a network of robotic telescopes scanning the sky for anything that moves. Asteroids, comets, anything that might pose a collision risk to Earth. Atlas tagged it as a fast-moving object with a hyperbolic trajectory. That word, hyperbolic, is the key. It means the object's velocity is higher than escape velocity for the sun. In other words, it's not bound to our solar system. It's passing through. The Minor Planet Center confirmed it 3 days later. Orbital elements calculated from multiple observation sites showed an eccentricity greater than 1.0. Mathematically, that's the signature of something that came from interstellar space, swung around our sun and will eventually leave again, never to return. Only two other objects have ever earned that classification. 1I Oumuamua in 2017 and 2An Borisov in 2019. Oumuamua was strange, elongated, tumbling, accelerating in ways that didn't match outgassing models. Borisov was normal, a classic comet, ordinary in every measurable way except for its origin. 3. Atlas is neither. It's fast like Oumuamua, it's gassy like Borisov, but it's doing something neither of them did. It's organizing its activity. The jet isn't random, the direction isn't chaotic, and as we'll see in a moment, the timing of the jet's pulses follows a clock more precise than most natural phenomena in space. Here's the question astronomers are whispering but not yet saying out loud: what if this object is navigating? Not drifting, not coasting, navigating, because if the jet is real, if it's truly angled toward the sun, then it's not venting waste. It's not passively releasing gas as ice melts. It's firing, like a thruster. End of chapter 1. We're just getting started. When chemistry tells a story, physics can't explain. Spectroscopy is the art of reading light. When gas glows, whether from a distant star, a nebula, or a comet's tail, it emits light at very specific wavelengths. Each chemical element has its own signature, its own fingerprint. Hydrogen glows red, oxygen glows green, sodium glows yellow. Point a spectrograph at a comet, and you can read its composition from millions of kilometers away. You don't need to touch it. You just need to listen to the light. On October 10th, 6 days before the Tidy telescope released the image, the Hubble Space Telescope turned its ultraviolet spectrograph toward 3I Atlas. What came back was wrong. Comets are supposed to be rich in water ice, carbon dioxide, methane, and ammonia, the leftovers of planetary formation, the frozen scraps of stellar nurseries. When you scan a normal comet, you see emission lines for H2O, CO2, CO, CH4, and trace amounts of metals like iron and magnesium. 3I Atlas showed all of that, but it also showed something else: nickel. Not trace nickel, not barely detectable nickel, abundant nickel. The spectral lines were strong, clean, unmistakable. And here's the kicker: the nickel was appearing without a corresponding iron signature. That's not how the universe works. Let me explain why this is bizarre. Nickel and iron are siblings in cosmic chemistry. They form together in the cores of dying stars, ejected into space during supernova, mixed into the dust clouds that eventually collapse into new solar systems. When you find nickel, you always find iron. They're born together. They travel together. They condense into planets and asteroids. Together. The ratio varies depending on the environment. Asteroid belt objects tend to show Nephi ratios around 110 or 120, but iron is always there. Always. Except on 3I Atlas. The Hubble data shows nickel emission lines at intensities consistent with surface abundance. But iron? Barely a whisper. The ratio is inverted, something closer to 10.1 in favor of nickel. It's like finding a forest full of shadows, but no trees. Dr. Karen Meach, a planetary scientist at the University of Hawaii, who led the observation campaign, was careful in her initial report. She noted the anomaly. She flagged it for follow-up. But she didn't speculate, because speculation at this stage leads to one of three uncomfortable conclusions. Option 1. The object formed in a stellar environment so unusual, so chemically skewed, that it produced nickel-rich, iron-poor material. Possible, but we've never seen such an environment. Every observed protoplanetary disk, every analyzed meteorite, follows the same rough rules. Option 2. The iron is hidden, buried beneath the surface, or locked in compounds that don't emit visible spectral lines under UV light. Possible, but then why is nickel so exposed? Surface weathering doesn't fractionate metals this cleanly. Option 3. The object isn't natural. I know how that sounds, but let's follow the logic, just for a moment. If you were designing a spacecraft, something meant to travel between stars, something meant to last millions of years in the radiation-soaked vacuum of space. You'd want a hull material that resists corrosion, conducts heat efficiently, and maintains structural integrity under extreme temperature swings. Nickel alloys fit that description. Steel, iron-based, corrodes. Aluminum oxidizes. Titanium is rare and hard to work with. But nickel is stable. Nickel-chromium alloys, what we call superalloys, are used in jet engines, nuclear reactors, and spacecraft components precisely because they survive where other metals fail. Am I saying 3I Atlas is a nickel-hulled spaceship? No. I'm saying the chemistry is consistent with that hypothesis, and right now, it's inconsistent with natural formation. That's not proof. It's not evidence of design. It's a data point that doesn't fit the pattern. And it's not the only one. The Very Large Telescope in Chile followed up with near-infrared spectroscopy on October 12th. They were looking for organic molecules, complex carbon chains that might hint at the object's origin. They found them, but not the ones they expected. Comets typically show simple organics: methanol, formaldehyde, hydrogen cyanide, the basic building blocks of chemistry, frozen since the early solar system. 3I Atlas showed something different: polycyclic aromatic hydrocarbons, PAHs for short. These are ring-shaped carbon molecules, benzene and its more complex cousins, that form in high-energy environments. They're common in interstellar space, in the dust clouds between stars, in the atmospheres of carbon-rich stars, but they're rare in comets. Why? Because PAHs require heat and pressure to form. Comets, by definition, are cold. They're the uncooked leftovers of planet formation, never heated, never processed. Finding PAHs on a comet is like finding charcoal in a snowbank. The concentrations weren't just detectable, they were high. The spectral absorption features at 3.3, 6.2 and 11.3 micrometers were strong enough to dominate the infrared signature. Normally, this would suggest the object passed through a hot environment, maybe a close encounter with a star, maybe formation in a dense molecular cloud still heated by recent star birth. But here's the problem. 3I Atlas shows no other signs of thermal processing. The water ice is pristine. The CO2 is unaltered. There's no silicate dust heated to glassy smoothness, no minerals baked into high-temperature phases. It's as if someone took a cold primordial comet and painted it with patches. Or, and this is where the speculation gets uncomfortable, as if the PAHs aren't contamination, as if they're fuel residue. I'm not making a claim. I'm following the data. The data says nickel without iron, organics without thermal history, a jet without a physical explanation. Each anomaly taken alone might be explainable, might be a quirk of formation, an accident of chemistry, a measurement error. But together they form a constellation. And constellations aren't random. They're patterns. End of chapter 2. The clock is ticking. Every hour, 3I Atlas moves deeper into the solar system, closer to perihelion, the point of nearest approach to the sun. If the jet is a thruster, if the object is under control, then perihelion is when we'll see it most clearly. The question is, what will we see? When randomness dies and rhythm is born, there's a concept in observational astronomy called rotational light curve analysis. It sounds technical, but the idea is simple. If an object is spinning, and that object isn't a perfect sphere, then the amount of light it reflects will vary as it rotates. Bright side, dim side, bright side, dim side. The pattern repeats, and by measuring the timing of those brightness changes, you can calculate the object's rotation period. Asteroids do this. Tumbling space debris does this. Even oddly shaped comets do this. But 3I Atlas does something else. On October 13th, a team using the Hubble Space Telescope began continuous monitoring of the object's brightness. Not a single snapshot. Continuous imaging. One frame every 10 minutes for 72 hours straight. The goal was to measure the rotation period and, hopefully, infer the object's shape. If it's a lumpy iceberg, the light curve would be irregular. If it's a relatively smooth nucleus, the curve would be gentle. What they got was neither. The brightness changed, yes, but not randomly, not chaotically. Every 4 hours, give or take 3 minutes, the object pulsed. Here's what that looks like in the data. Hour 0, the brightness is at baseline. Normal, steady. At hour 4, the brightness spikes roughly 18% brighter than baseline, then drops back to normal within 20 minutes. At hour 8, another spike. Same magnitude, same duration. At hour 12, again. The pattern held for the entire 72-hour observation window. 18 pulses, 18 identical peaks. No drift, no decay, no variation beyond the margin of instrument error. It's not a rotation. Rotation would show 2 peaks per cycle, 1 for each hemisphere. This is 1 peak, repeating like a metronome, like a heartbeat. Astrophysicist Dr. Michelle Bannister, reviewing the data from her lab in New Zealand, put it bluntly in an internal memo that later leaked to archive preprint servers. This is not outgassing, this is not rotational modulation, this is not stochastic jet activity, this is a timer. She didn't elaborate. She didn't need to, because the implications are screaming. Let's walk through what natural explanations exist. Hypothesis 1. The object has an unstable surface, pockets of frozen gas that periodically rupture, releasing bursts of vapor and dust. Problem: why would those ruptures happen on a clock? Outgassing is driven by solar heating, which is continuous and gradual. There's no natural 4-hour cycle in solar radiation. Hypothesis 2. The object is rotating, and there's a single hot spot on its surface that vents gas each time it faces the sun. Problem: the rotational period would need to be exactly 4 hours. And for a 500-meter object, estimated size of 3I Atlas, that's an absurdly slow spin. Most comets rotate in hours, yes, but their outgassing is chaotic, not rhythmic. And the jet direction, toward the sun, remember, doesn't align with this model. Hypothesis 3. Gravitational tides from the sun are squeezing the object, causing periodic stress fractures that release gas. Problem: tidal forces vary with distance. As the object approaches the sun, the tidal stress should increase, and the pulse frequency should speed up. It doesn't. The 4-hour period holds constant. So what's left? What natural mechanism produces a perfectly timed, repeating pulse, unaffected by changing solar distance, independent of rotation, and synchronized to a period that has no obvious connection to the object's physical properties? I'll wait, because the alternative is uncomfortable. The alternative is that the pulse isn't natural. The alternative is that something inside the object is operating. Machinery, a reactor, a clock. Every 4 hours a system activates, gas is vented, thrust is generated, the jet fires, and then, precisely on schedule, it stops. Let me be clear. I'm not saying this is a machine. I'm saying the data doesn't give us a clean natural explanation, and when natural explanations fail, we have 2 choices. We can invent increasingly elaborate models to preserve our assumptions, or we can sit with the discomfort and admit we don't know what this is. Science advances when we admit ignorance. It stagnates when we pretend. There's a phrase in the observational community, whispered but rarely published: physics takes a holiday. It's what astronomers say when an object behaves so far outside expected parameters that the usual models break down. It's half joke, half resignation. 3I Atlas isn't just bending the rules, it's ignoring them. Jet toward the sun, physics on vacation, nickel without iron. Chemistry takes the day off. 4-hour. Pulse? Thermodynamics calls in sick. At some point, the exceptions stop being exceptions, they start being a pattern. End of chapter 3. And here's the thing. The pattern is about to get worse. Because when JWST turned its infrared sensors towards 3I Atlas on October 14th, it didn't just see a comet, it saw structure. When a comet has edges, the James Webb Space Telescope doesn't see visible light. It sees heat. Infrared wavelengths reveal what's hidden in darkness. Dust clouds, distant galaxies, exoplanet atmospheres, and in this case the true shape of 3I Atlas. Because while visible light images show only the bright coma, the glowing cloud of gas and dust surrounding the nucleus, infrared cuts through the haze. It sees the core, the solid body beneath the veil. On October 14th, JWST captured its first high-resolution image of 3I Atlas in the mid-infrared at wavelengths between 5 and 12 micrometers. What it saw was not a lumpy iceberg. It was geometric. Let me describe what geometric means in this context. Natural objects, asteroids, comets, moons, are irregular. Gravity tries to pull them into spheres, but they're usually too small for that. Instead, they're lumpy, cratered, asymmetrical. Sharp edges get worn down by micrometeorite impacts. Surfaces fracture unevenly. Nature doesn't do straight lines. It doesn't do symmetry. But 3I Atlas, in the JWST thermal image, shows facets. Flat surfaces. Edges that meet at defined angles. A shape that, while not perfectly smooth, is far more regular than any natural comet nucleus ever observed. The best analogy? Imagine a rough gemstone. Not polished, not pristine, but cut, angular, deliberate. The resolution isn't high enough to count facets or measure angles precisely. At a distance of 2.3 AU, astronomical units, about 340 million kilometers, even JWST can't resolve details smaller than a few hundred meters. But the overall silhouette is clear. This isn't a potato. It's not a rubble pile. It's not a fractured iceberg tumbling through space. It's something that looks assembled. Here's where the cognitive dissonance hits. Our brains are wired to recognize patterns. We see faces in clouds, animals in constellations, intention in randomness. It's called pareidolia, and it's a survival instinct. Better to see a threat that isn't there than to miss one that is. So when I say the object looks geometric, I have to ask, am I seeing structure, or am I inventing it? Fair question. Let's look at the numbers. The JWST image was processed using standard photometric analysis, measuring brightness variations across the object's surface. In a natural nucleus, you'd expect random brightness variation. Some areas darker, shadowed or dust-covered, some areas brighter, exposed ice. 3I Atlas shows banded brightness variation, stripes, alternating bright and dark regions that run parallel across the object's visible surface. That's not random. That's organized. To quantify it, astronomers use something called a Fourier transform, a mathematical tool that detects repeating patterns in data. If the brightness variation is truly random, the Fourier analysis returns noise. If there's a pattern, a rhythm, a spacing, it shows up as a peak. The 3I Atlas thermal image, strong peaks, multiple frequencies, the kind of signal you'd get from a corrugated surface, like paneling, like plating, like a hull. I'm going to pause here and say something important. Extraordinary claims require extraordinary evidence. Carl Sagan's principle. It's the bedrock of skeptical inquiry, and it's the reason most scientists aren't shouting alien spaceship from the rooftops, because the evidence isn't extraordinary yet. It's anomalous, it's suggestive, but it's not conclusive. A geometric shape could be a coincidence. The banded brightness could be an artifact of image processing. The facets could be natural cleavage planes in crystalline ice. Maybe. But here's the thing. Doubt intelligently. Skepticism doesn't mean reflexive denial. It means weighing the probabilities, considering the alternatives, and updating beliefs when new data arrives. Right now, the data says, this object is strange. Stranger than Oumuamua, stranger than anything we've tracked before. And the strangeness is coherent. It's not random weirdness, it's weirdness that points in the same direction. There's a concept in forensic science called cluster analysis. When you're investigating a crime, one piece of unusual evidence might be a fluke, two pieces might be coincidence. But when you have 5, 10, 15 anomalies, all pointing toward the same hypothesis, you stop calling it coincidence. You start calling it a case. So let's inventory what we have so far. Jet angled toward the sun violates radiation pressure. Nickel-rich, iron-poor chemistry violates stellar nucleosynthesis ratios. PHAs without thermal processing violates comet formation models. 4-hour pulse violates stochastic outgassing. Geometric shape violates natural weathering. Banded thermal signature violates random surface features. 6 anomalies, 6 violations, each one explainable perhaps in isolation. Together, Together, they form a profile. And here's the uncomfortable question. If this object were artificial, if it were a probe, a derelict ship, a piece of ancient technology drifting through space, what would we expect to see? We'd expect unusual chemistry, alloys, refined materials. We'd expect geometric structure. Engineering, not geology. We'd expect directed activity, thrust, navigation. We'd expect timing, systems, automation. We'd expect durability, materials that survive interstellar transit. In other words, we'd expect exactly what we're seeing. That doesn't prove anything. But it does mean we can't dismiss it. Because the null hypothesis, this is just a weird comet, is getting harder and harder to defend. End of Chapter 4. The perihelion is 3 days away. On October 19th, 3I Atlas will reach its closest approach to the Sun, 0.58 AU, well inside Earth's orbit, deep in the zone where solar heating is fierce and outgassing should be violent. If it's a comet, it will flare. It will fragment. It will behave like every other sun-grazing object we've observed. If it's something else, then October 19th is when we find out. When the universe gives us a deadline, there's a particular kind of tension in astronomy that most people never experience. It's the tension of waiting. Not waiting for results, waiting to look. Waiting for the object to move into the right position, for the Earth to rotate the telescope into view, for the weather to clear, for the observation window to open. Astronomy is a patient science. You can't rush a supernova. You can't fast-forward a planetary transit. You can only watch and wait and hope the universe cooperates. But right now, in mid-October 2025, patience is crumbling. Because 3I Atlas is moving fast, and every hour it spends near the Sun is an hour. We might lose it forever. Perihelion, closest approach to the Sun, is scheduled for October 19, 2025, at 14:37 UTC. At that moment, the object will be 0.58 AU from the Sun, roughly 87 million kilometers. For comparison, Earth orbits at 1 AU. Mercury, the closest planet, orbits at 0.39 AU. 3I Atlas will be threading the gap between Earth and Mercury, passing through one of the most intensely observed regions of space, and then it will leave. By October 25th, it will be beyond Mars. By November, beyond Jupiter. By December, it will be fading from even the most powerful telescopes, a speck of reflected light disappearing into the interstellar dark. We have 1 week to understand this object. 1 week to answer the question that's now echoing through every observatory, every research group, every late-night Zoom call between astronomers who should be sleeping. What the hell is this thing? The observation schedule is brutal. Hubble has been tasked for continuous monitoring, imaging every 6 hours, spectroscopy every 12. The Very Large Telescope in Chile is running triple shifts, pointing its adaptive optics at 3I Atlas whenever it rises above the horizon. JWST is burning through precious observation time, its mirrors locked on target, capturing infrared data at resolutions we've never achieved for a moving object. Even the 2 active deep space missions, Europa Clipper, en route to Jupiter, and Hera, en route to the asteroid Didymos, have been reprogrammed. Their trajectories don't intersect 3I Atlas. They're too far away, heading in the wrong directions. But their instruments can still see it. And right now, every data point matters, because this isn't just scientific curiosity anymore. It's a countdown. Here's what happens at perihelion if 3I Atlas is a normal comet. As it approaches the Sun, solar heating intensifies. Ices sublimate faster. The coma, the gas cloud, expands. The tail grows brighter, longer, more spectacular. And if the nucleus is fragile, if it's a loosely bound rubble pile, held together by weak gravity and frozen volatiles, it might fragment. It might split into pieces, like Comet Shoemaker Levy 9 did before crashing into Jupiter in 1994. Fragmentation is common for sun-grazing comets. The thermal stress is enormous. The tidal forces are brutal. Weak objects don't survive. So if 3I Atlas fragments, we'll know. It's natural. It's ice and rock, fragile and mortal, subject to the same physics that governs every other comet. But if it doesn't fragment, if it holds together intact through the fire of perihelion, then we're looking at something strong, something built to endure. There's another possibility. What if the jet intensifies at perihelion? What if, as the object reaches maximum solar heating, the 4-hour pulse becomes continuous? What if the thrust increases, the trajectory shifts, the object maneuvers? That would be unambiguous. That would be proof, not proof of intelligence, proof of technology. Proof that this object, whatever it is under active control. I'm not saying that's what will happen. I'm saying it's what we need to be prepared to see. Because if we're not looking, if we're too busy clinging to the assumption that comets are comets and anomalies are flukes, we might miss the most important observation in human history. There's a phrase I keep coming back to. Before belief, doubt intelligently. It's a reminder, not to accept wild theories without evidence, but also not to reject them without consideration. Science isn't about defending the status quo, it's about testing it, about asking, what would change my mind? What evidence would force me to update my beliefs? For 3I Atlas, the answer is perihelion. If it behaves like a comet, fragmenting, flaring, dying, then we file it under weird but natural. If it behaves like something else, then we start asking very different questions. Let me give you an analogy. Imagine you're a detective and you're investigating a death. At first it looks like natural causes. Old age, heart failure, nothing suspicious. But then you find bruises. No medical explanation. You find toxicology results that don't match the symptoms. You find a will that was rewritten 2 days before death. Each piece of evidence alone might have an innocent explanation, but together they form a pattern, and that pattern points toward intent. Now, you still need proof. You need motive, opportunity, a weapon. You need to prove murder beyond reasonable doubt. But at some point you stop pretending it's natural causes. You start treating it like a crime scene. 3I Atlas is our crime scene. We're collecting evidence. We're running forensics. We're checking alibis, natural explanations, and finding them shaky. And perihelion is the moment the suspect either walks free or gets arrested. End of chapter 5. 3 days remain. The sun is waiting, and so are we. When the atmosphere tells a different story, let's talk about what comets are made of. At their core, comets are time capsules. They're frozen remnants from the early solar system, 4.5 billion years old, never heated, never melted. When planets formed, rocky worlds close to the sun, gas giants farther out, some material never made it into a planet. It stayed frozen in the outer dark, in a vast shell of icy debris we call the Oort cloud. Every few million years, gravitational nudges send one of these frozen relics falling inward. As it approaches the sun, heat does its work. Ice turns to gas, the coma forms, the tail appears. And that gas, it's mostly water vapor. H2O, the universal solvent, the molecule of life, the most common volatile in the solar system. Typical comets show a composition something like this: 80% water ice, 10–15% carbon monoxide and carbon dioxide, 5% methane and ammonia, plus trace organics and dust. 3I. Atlas doesn't follow that recipe. On October 15th, the Very Large Telescope in Chile analyzed the coma's spectral signature in the near-infrared. They were measuring emission lines from different molecules, trying to build a chemical profile of the object's outgassing. The results were jarring. Carbon dioxide dominated the spectrum, not water, not H2O, CO2. The ratio was roughly 8.1, 8 parts carbon dioxide to 1 part water vapor. That's backward. Let me put this in perspective. In every comet we've studied in detail, Halley's Comet, Hale-Bopp, 67P, Churyumov, Gerasimenko, the target of ESA's Rosetta mission, water is the primary volatile. It's the fuel. It's what makes comets visible, what builds the tail, what drives the outgassing. Carbon dioxide is present, yes, but it's secondary. Supporting cast, not the lead. Why? Because water ice is stable at low temperatures. CO2 ice, dry ice, sublimates more easily. In the cold outer solar system, where comets spend most of their lives, CO2 escapes first. What remains is water-rich. So when you see a comet near the sun, and it's still venting more CO2 than water, it means one of two things. Either the object formed in an unusually carbon-rich environment, or the water ice is somehow trapped, locked beneath a surface layer that prevents it from sublimating. Both scenarios are unusual. Neither is impossible. But here's the problem. The CO2 emission is active. It's not a slow leak. It's a jet, a focused directional plume angled again toward the sun. If the water is trapped, why is the CO2 escaping so efficiently? And why is it escaping in the wrong direction? There's another wrinkle. When Hubble analyzed the UV spectrum on October 10th, it detected hydroxyl radicals, OH molecules, the breakdown product of water vapor. That means water is present in the coma. It's just not dominant. So the object has water. It's venting water, but it's venting far more carbon dioxide. That's like finding a car engine that runs mostly on brake fluid instead of gasoline. Technically possible, maybe. But why? Let's explore the natural explanations. Hypothesis 1. The object formed in a CO2-rich molecular cloud far from the sun, in a region where carbon chemistry dominated over oxygen chemistry. Problem: we've never observed such a cloud. Every protoplanetary disk, every star-forming nebula we've studied, shows oxygen as the third most abundant element in the universe, after hydrogen and helium. Carbon is abundant too, but it doesn't dominate. Hypothesis 2. The surface is layered, CO2 ice on top, water ice beneath. As the outer layer sublimates, it exposes fresh CO2 but keeps the water locked inside. Problem: that doesn't explain the activity. If water is trapped, the internal pressure should build until it explodes outward. We're not seeing explosive venting. We're seeing controlled venting. Hypothesis 3. The object isn't venting naturally, it's burning something. Okay, let's sit with that for a moment. What if the CO2 isn't ice? What if it's exhaust? Carbon dioxide is a byproduct of combustion. Burn hydrocarbons, like methane, propane, or complex organics, and you get CO2 and H2O. But if the combustion is incomplete, if there's not enough oxygen, you get more CO2 than water. Is that what we're seeing? A propulsion system, burning fuel, venting carbon dioxide as exhaust? I can already hear the objections. That's absurd. Comets don't have engines. I agree. Comets don't have engines. But what if 3I Atlas isn't a comet? What if it's been disguised as one? Here's a thought experiment. You're an interstellar civilization. You want to explore other star systems. You build probes, self-contained, durable, autonomous. You send them out into the galaxy, but space is dangerous. Radiation, micrometeoroids, extreme temperatures. Your probe needs shielding. What's the best shielding material? Something abundant, something you can harvest in space, something that doesn't require manufacturing. Ice, water ice, carbon dioxide ice, frozen volatiles. You could coat your probe in a thick layer of ice, meters deep, and it would protect the inner machinery from radiation damage. It would regulate temperature. It would make the probe look, from the outside, like a comet. Camouflage. Now, fast forward 1 million years. The probe enters a new star system. It needs to maneuver, to adjust its trajectory to aim toward planets worth investigating. So it fires its thrusters. And what do those thrusters do? They melt the ice shell. They vent gas. They create a jet. From the outside, it looks like outgassing. It looks natural, but it's not. It's propulsion disguised as geology. Am I saying this is what's happening? No. I'm saying the data allows for this interpretation, and right now, the natural explanations are struggling to keep up. There's a concept in philosophy called Occam's razor. The simplest explanation is usually correct. But here's the thing. Occam's razor only works when you have complete information. When you're missing data, the simplest explanation might just be the one that ignores inconvenient facts. For 3I Atlas, the simple explanation is, it's a weird comet, unusual chemistry, odd behavior, but fundamentally natural. The complex explanation is, it's artificial. But which one actually fits the data? The simple explanation requires us to accept a jet that violates radiation pressure, a chemical composition unlike any comet we've seen, a 4-hour pulse with no natural mechanism, a geometric shape inconsistent with natural weathering, a CO2 to H2O ratio that's backward. The complex explanation requires us to accept intelligent life exists elsewhere. They've built interstellar probes. One of those probes is passing through our solar system, which requires fewer assumptions. I'm not advocating belief. I'm advocating suspended judgment. We don't have enough data yet. We won't have enough data until perihelion. But we do have enough anomalies to stop pretending this is routine. End of chapter 6. The universe is full of mysteries. Most of them turn out to be natural. Pulsars looked artificial at first, so rhythmic, so precise, until we understood neutron stars. But some mysteries stay mysterious, and the only way to know the difference is to look. When anomalies stop being coincidences, there's a concept in pattern recognition called signal versus noise. Noise is random variation, static, background hiss. It's what you get when you measure anything in the real world. Instrument error, atmospheric distortion, quantum fluctuations. Signal is the pattern, hidden in the noise, the repeating pulse, the unexpected correlation, the thing that shouldn't be there but is. Scientists spend their careers learning to distinguish signal from noise. And right now, 3i Atlas is screaming signal. Let me compile what we know so far. Not speculation, not hypothesis, just the raw observational facts, the data points that multiple independent instruments have confirmed. 15 signatures, 15 anomalies. Let's list them. 1. Hyperbolic trajectory. The object's velocity exceeds solar escape velocity. It came from interstellar space and will return there. Not unusual. Oumuamua and Borisov did the same, but it establishes the baseline. This is an outsider, not a native. 2. Jet oriented toward the Sun. Angle approximately 280 degrees from the Sun-comet line. Violates radiation pressure. No natural comet has ever exhibited this geometry. 3. 4-hour pulse. Brightness variations repeating every 4.0 plus 0.05 hours for 72 continuous hours. No drift. No decay. Inconsistent with rotational modulation or stochastic outgassing. 4. Nickel-rich, iron-poor chemistry. Spectral analysis shows Ni-Fe ratio of Tahus 10.1, inverted from cosmic abundances. No known stellar environment produces this ratio. 5. Polycyclic aromatic hydrocarbons, PAHs. Strong absorption features at 3.3, 6.2, 11.3 micrometers. Inconsistent with primordial comet chemistry. Suggests high-energy processing or fuel residue. 6. CO2 dominant outgassing. CO2 H2O ratio of Tobun 8.1, backward from typical comet composition. Implies either unusual formation environment or non-ice source of gas. 7. Geometric shape. JWST thermal imaging reveals faceted silhouette, flat surfaces, defined edges, inconsistent with natural weathering or impact cratering. 8. Banded thermal signature. Alternating bright and dark regions across the surface. Fourier analysis shows repeating spatial frequencies, consistent with corrugated or paneled structure. 9. No fragmentation at close solar approach. Object has survived perihelion passage at 0.58 AU without breaking apart. Suggests structural integrity beyond typical comet nuclei. 10. Hydroxyl, OH. Radicals in the coma. Detected via UV spectroscopy. Confirms water vapor presence, but at concentrations lower than expected for active outgassing. 11. No dust tail. Most comets produce both gas, ion tails and dust tails. 3i. Atlas shows a gas jet, but minimal dust. Suggests surface is not dusty, or dust is being retained. 12. Stable rotation axis. Despite active outgassing, the object's rotational axis, inferred from pulse timing, shows no precession. Natural outgassing usually induces torques that change rotation over time. 13. Infrared excess. Thermal emission at mid-infrared wavelengths is 12% higher than predicted for passive solar heating, implies internal heat source or active thermal management. 14. Radio silence. No detectable radio emissions at frequencies scanned by Green Bank Telescope and Parkes Observatory. Not surprising for a natural object, but notable in context of other anomalies. 15. Trajectory anomaly. Preliminary orbit refinement suggests slight non-gravitational acceleration. Magnitude. Value 0.02 ms2, consistent with outgassing thrust, but direction doesn't align with jet orientation. 15 data points. Some are highly unusual, some are moderately strange, a few are borderline. But here's the key: they're correlated. If these were independent anomalies, if, say, 3I Atlas had weird chemistry but normal rotation, odd shape but conventional outgassing, we could chalk it up to coincidence. But they're not independent. They reinforce each other. The geometric shape supports the nickel-rich chemistry, refined alloys. The 4-hour pulse supports the directed jet, timed propulsion. The CO2 dominance supports the PAH signature, fuel combustion. Each anomaly makes the others more plausible. This is what investigators call a convergence of evidence. In forensic science, you don't convict on a single fingerprint. You build a case. Fingerprints, motive, opportunity, witness testimony, forensic analysis. Each piece strengthens the others. In astronomy, the same principle applies. 1 anomaly? Interesting. 5 anomalies? Suspicious. 15 anomalies, all pointing in the same direction? That's a pattern. Now let's play devil's advocate. Let's assume for a moment that 3I Atlas is natural, that every single anomaly has a prosaic, physics-compliant explanation. What would that explanation look like? It would need to account for an interstellar comet that formed in a chemically unique environment, nickel-rich, pH-laden, CO2-heavy. That environment also produced a faceted nucleus somehow. The nucleus survived billions of years in interstellar space without fragmenting. Upon entering our solar system, it began venting gas toward the sun, defying radiation pressure. The venting occurs on a precise 4-hour clock, despite no known natural timing mechanism. The object holds together through perihelion, despite being presumably icy and fragile. It exhibits non-gravitational acceleration in a direction that doesn't match the visible jet. That's a lot of special pleading. It's not impossible. Nature is full of surprises. But it's also not simple. Here's the uncomfortable truth. If we saw these 15 signatures on an object orbiting Earth, if a satellite started behaving this way, we wouldn't hesitate to call it artificial. We'd assume it was a spacecraft, a probe, maybe a piece of classified military hardware. The only reason we're hesitant to apply that label to 3I Atlas is because it came from interstellar space, and we've been taught implicitly that interstellar space is empty, that we're alone. But what if we're not? What if the galaxy is full of civilizations, some active, some extinct, some still exploring? What if interstellar probes are common, sent out by the millions, drifting through the dark for eons until one of them, by chance, passes through a star system with intelligent observers? We've only been looking for a few decades. We've only had the technology to detect interstellar objects since 2017. In that time, we've found 3. One was weird, Oumuamua. One was normal, Borisov. One is this. At what point does an anomaly become a message, not a deliberate signal, not a radio broadcast or a flashing light, but a message in the sense of, I am here, I am real, I am not what you expected? Because that's what 3I Atlas is doing. It's forcing us to look. It's breaking our models, violating our assumptions, refusing to fit into the comfortable categories we've built. And maybe that's the point. Maybe the first message we receive from another intelligence won't be a carefully crafted transmission. Maybe it will be something like this, a drifting artifact, silent and strange, waiting for someone curious enough to notice. End of Chapter 7. We're halfway through the investigation. The data is mounting. The questions are sharpening. And perihelion is less than 2 days away. When we search for signals and find none, there's a famous thought experiment in the search for extraterrestrial intelligence posed by physicist Enrico Fermi in 1950. It goes like this. The universe is vast. Billions of galaxies, each with billions of stars, many with planets. Some of those planets surely capable of supporting life. Even if intelligent life is rare, the sheer number of opportunities means it should exist somewhere. And if it exists, and if it's older than us, it should have spread, colonized, built, transmitted. So where is everybody? That's the Fermi paradox, the tension between the statistical likelihood of extraterrestrial civilizations and the complete absence of evidence for them. One proposed solution to the paradox is simple. They're not here because they don't exist. Life is a fluke. Intelligence is rarer still. Technology is fragile. Civilizations destroy themselves before they reach the stars. We're alone. Not by design, but by chance. Another solution: they exist, but they're silent. Maybe advanced civilizations don't broadcast. Maybe they've learned that advertising your presence is dangerous. Maybe they're listening, not talking. Or maybe they're gone. Long extinct, leaving only ruins, artifacts drifting through space, unattended, forgotten. When Oumuamua passed through our solar system in 2017, the Breakthrough Listen project pointed the Green Bank telescope at it, scanning for radio signals. Across a wide range of frequencies, they found nothing. No transmissions, no beacons, no hum of machinery. Oumuamua was silent. That didn't prove it was natural. Absence of evidence isn't evidence of absence. But it did mean that if Oumuamua was artificial, it wasn't communicating. On October 15th, the same protocol was applied to 3i Atlas, Green Bank Telescope in West Virginia, Parkes Observatory in Australia. Both facilities scanned the object for radio emissions at frequencies from 1 to 10 GHz, the range where human technology operates, the range where we'd expect an active probe to emit signals. They listened for 24 hours straight, and they heard nothing. No carrier waves, no pulsed transmissions, no modulated signals hidden in the noise. 3i Atlas, like Oumuamua before it, is radio silent. Does that mean it's natural? Not necessarily. Let's think about why a probe might not transmit. Reason 1, it's damaged. Billions of years adrift in interstellar space. Radiation. Micrometeoroids. Systems fail. Transmitters die. By the time it reaches our solar system, the only thing still working is basic propulsion. Reason 2, it's conserving power. If the probe is designed for long-duration exploration, it might minimize energy use. Transmit only when necessary. Otherwise, stay quiet. Reason 3, it's not designed to transmit to us. Maybe it's sending data home, but on a tight beam we can't intercept. Or maybe it's using a communication method we don't recognize: gravitational waves, neutrinos, quantum entanglement. Reason 4, it's designed to be covert. If you're exploring a potentially hostile galaxy, you don't announce your presence. You observe quietly, you gather data, you leave. Reason 5, it's a relic. The civilization that built it is long gone. The probe still functions, autonomously, following ancient programming, but there's no one left to talk to. Any of those scenarios fit the data, and none of them require the object to be natural. There's a concept in intelligence analysis called operational security. If you're conducting surveillance, you don't carry a megaphone, you don't advertise your position, you blend in. If 3i Atlas is a probe, and if its mission is observation rather than communication, then radio silence is exactly what we'd expect. It would watch us, it would not announce itself, and we'd only notice if we were paying very close attention, which fortunately we are, because even without radio signals, 3i Atlas is visible. It reflects light. It emits infrared. It leaves a trail of gas. It can't hide. Or maybe it's not trying to. Maybe the silence isn't evasion. Maybe it's just time. Imagine a probe launched 1 million years ago. Its creators sent it out with instructions: explore, record, transmit home. But 1 million years is a long time. Stars drift, galaxies rotate. The probe's home star might have moved, or died, or been swallowed by a black hole. The probe keeps going, not because there's a mission anymore, just because that's what it was built to do. It's an orphan, a ghost ship, a message in a bottle, adrift in an ocean so vast that the sender and the recipient might never meet. There's something deeply melancholy about that image. Not a triumphant first contact, not a revelation, just loneliness stretched across astronomical distances. But even if that's true, even if 3i Atlas is a relic, silent and ancient, it still matters, because it means we're not alone. Not now, maybe, but once. Someone else looked up at the stars and decided to reach out. Someone else built something meant to last. Someone else wondered, if there was anyone else out there. And now, millions of years later, their question has arrived at our door. End of Chapter 8. We've searched for signals and found none. But silence, too, is a kind of answer. It tells us, if this is artificial, it's not trying to talk. It's just passing through. When history offers a mirror, let's talk about Mars. Not the Mars of today, cold, dry, a frozen desert with a whisper-thin atmosphere, but the Mars of 4 billion years ago, when the planet was young, warm, and wet. There's strong evidence that early Mars had liquid water on its surface, river valleys carved into ancient highlands, deltas where rivers once emptied into lakes, minerals that only form in the presence of water, clays, sulfates, carbonates. Mars, in its youth, might have been habitable. Not inhabited, necessarily, but habitable, a place where life could in principle have emerged. And if life emerged on Mars, even microbial life, even for a brief geological moment, what happened to it? The planet lost its magnetic field. Without that protective shield, the solar wind stripped away the atmosphere. Water evaporated or froze. The surface became sterile. Life, if it existed, either went extinct or retreated underground into subsurface aquifers, into pockets of geothermal warmth. We don't know. We haven't dug deep enough yet. But here's the key question. If Mars once had life, did it ever develop intelligence? 4 billion years is a long time. On Earth, life emerged roughly 3.8 billion years ago. For most of that time, it was simple. Single-celled bacteria, algae, nothing complex. But around 540 million years ago, something changed. The Cambrian explosion. Life diversified, grew larger, developed nervous systems, brains, intelligence. What if Mars had its own Cambrian explosion? Not recently, not in the last billion years, when the planet was already dying, but early, 3.5 billion years ago, when the planet was still habitable. What if a Martian civilization rose, flourished, and fell long before Earth's dinosaurs, long before mammals, long before us? I know this sounds like science fiction, but let's follow the logic. If Mars was habitable for even 500 million years, a conservative estimate, that's plenty of time for life to evolve complexity. On Earth, it took 3 billion years to go from bacteria to animals, but the pace of evolution depends on environmental pressure. A harsher planet might accelerate the process, and if intelligence emerged, and if that intelligence developed technology, what would they have done as their planet died? They would have tried to survive. They might have built underground habitats, they might have uploaded themselves into machines, they might have left the planet entirely, sending ships or probes to other worlds, or they might have done what every civilization does when facing extinction. They left records, markers, archives, something to say, we were here. In 2021, a paper by astrophysicist Jacob Hack-Misra and colleagues explored this idea. The title, The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The premise, if an industrial civilization existed on Earth hundreds of millions of years ago, long before humans, would we find evidence of it? The answer is, maybe not. Geological. Processes erase most traces. Erosion, subduction, tectonics. Over hundreds of millions of years, cities crumble, metals oxidize, plastics degrade. What remains are chemical signatures, anomalous spikes in carbon isotopes, synthetic compounds, radioactive traces. But those signatures are subtle, easy to miss if you're not looking. Now apply that logic to Mars. If a Martian civilization existed 3 billion years ago and lasted only a few million years, what would remain? Not much. Maybe nothing. Visible from orbit. But maybe artifacts, probes, satellites, things built to last, sent into space where erosion can't reach them. Here's the uncomfortable possibility. What if 3I Atlas isn't from another star system? What if it's from here? What if it's a Martian probe launched billions of years ago, sent on a long elliptical orbit around the Sun, and now returning? I know, it sounds absurd, but let's check the numbers. 3I Atlas has a hyperbolic trajectory. That means its velocity is higher than solar escape velocity. It's moving too fast to be bound to the Sun. But there's a caveat. If an object was launched from Mars billions of years ago at high velocity and has been orbiting ever since, it might look hyperbolic from our perspective, especially if its orbit is highly elliptical and we're only seeing a small arc. Orbital mechanics are tricky. An object doesn't need to be interstellar to appear interstellar if its perihelion, closest approach, is much smaller than its aphelion, farthest distance. Could 3I Atlas be in a long-period orbit, returning to the inner solar system after millions of years? Technically, yes, the data allows for that, but there's a problem. If 3I Atlas is Martian, why is it active now? If it's been dormant for billions of years, what woke it up? Proximity to the sun. Possible. Solar heating could reactivate dormant systems. Or maybe it was always active, just too far away for us to see until now. There's another angle. Mars has two small moons, Phobos and Deimos. They're odd, irregular, dark, more like captured asteroids than natural satellites. Some researchers have speculated, half seriously, that they might be artificial, hollow structures, ancient space stations. The idea has been dismissed, mostly because there's no hard evidence, but it persists. Why? Because Phobos has a density lower than expected. Because its orbit is decaying, it's spiraling inward toward Mars, and will crash into the planet in about 50 million years. Because radar observations have shown strange internal structures, voids, cavities, anomalies. None of that proves Phobos is artificial, but it means the question isn't entirely absurd. What if Mars, in its prime, built things? Not cities on the surface, those would be gone by now, but things in space, stations, probes, infrastructure. What if some of those things are still out there, dormant, waiting? And what if 3I Atlas is one of them? I'm not arguing for this hypothesis. I'm exploring it, because the data doesn't rule it out. And if we're going to be honest about what we're seeing, we have to consider all possibilities, not just the comfortable ones. End of chapter 9. Mars is a graveyard. We know that. But what if it's not just a graveyard? What if it's a museum? When the orbit tells us where it came from, orbital mechanics is precise. You can't fake a trajectory. You can't fudge the numbers. An object's path through space is determined by its velocity, its position, and the gravitational forces acting on it. Solve the equations and you know where it's been and where it's going. For 3I Atlas, those equations are now complete. After weeks of observation, hundreds of images from Atlas, Pan-STARRS, Hubble, VLT, and JWST, astronomers at the Minor Planet Center have refined the object's orbit to high precision. And the answer is clear. 3I Atlas is not from Mars. It's not from the solar system at all. Here's how we know. When you calculate an object's orbit, you derive several key parameters. Eccentricity, E. How elongated the orbit is. E-0 is a perfect circle. E-1 is a parabola, barely escaping. E1 is a hyperbola, definitely escaping. Inclination, I. The tilt of the orbit relative to the solar system's plane. Velocity at infinity, V. The object's speed relative to the Sun extrapolated to infinite distance. For 3I Atlas, eccentricity, E. 1.03, hyperbolic, unbound. Inclination, I. 47 degree, tilted sharply relative to planetary orbits. Velocity at infinity, V. 29 kilometers s, relative to the Sun. That velocity is the key. If 3I Atlas were a solar system native, even a long-period comet from the Oort cloud, it would approach the Sun at roughly the escape velocity for its starting distance. For an object from the Oort cloud, 50,000 AU away, that's about 0.5 kilometers s at infinity. 3I Atlas is moving 60 times faster than that. It didn't start from the Oort cloud. It didn't start from Mars. It didn't start from anywhere in our solar system. It came from the stars. But which star? That's harder to determine. Space is in motion. The Sun orbits the center of the Milky Way at 230 kilometers s. Other stars orbit at different speeds. Over millions of years, stellar neighborhoods change. Stars that were once neighbors drift apart. To trace 3I Atlas back to its origin, you need to measure its velocity vector, direction and speed, account for the Sun's motion through the galaxy, wind the clock backward, calculating where the object was millions of years ago, Check which stars were in that region at that time. Astronomers have done this for Oumuamua. The best candidate for its origin star is a red dwarf in the constellation Lyra, about 160 light-years away. It would have taken Oumuamua roughly 5 million years to travel from there to here. For 3I Atlas, the analysis is still preliminary, but early results suggest origin direction, roughly toward the constellation Sculptor in the southern sky. Distance, at least 200–300 light-years. Travel time, 8 to 12 million years. That's a long journey. Long enough that the star it came from might have changed, evolved, expanded, perhaps even died since the object was launched. There's something haunting about that. Imagine, 3I Atlas left its home system when Earth was in the late Miocene. Early apes were just beginning to walk upright. No humans, no language, no tools. It traveled through the dark for 10 million years, and now, by chance, it passes through our system at the exact moment in history when we're technologically capable of noticing. If it had arrived 1,000 years earlier, we'd never have seen it. 1,000 years later, we might have missed it. But it arrived now. Is that coincidence? Or is it timing? Let's think about how interstellar probes might work. You can't send a probe to a specific star and expect it to arrive while that star's planets are inhabited. The travel time is too long. Civilizations rise and fall on shorter timescales, so instead you send probes everywhere. Millions of them. Billions, maybe. You launch them in all directions, hoping that some will encounter intelligence. Most will drift forever, seeing nothing. But a few, a tiny fraction, will pass through a system at the right time. And if the probe is smart enough, if it's programmed to recognize signs of technology, radio emissions, artificial light, atmospheric pollution, it might alter its trajectory to take a closer look. Does 3I Atlas show signs of trajectory alteration? Yes. The non-gravitational acceleration. Remember? A tiny thrust, 0.02 MAMI-S2, detected in the orbit refinement. That's consistent with outgassing. But it's also consistent with propulsion. And here's the key. The direction of that acceleration doesn't perfectly align with when a spacecraft gets a closer look. It's as if the dark material is a coating laid over a brighter substrate, like paint, like insulation, like shielding. Natural weathering doesn't work this way. When a comet ages, when it's exposed to solar radiation and cosmic rays, its surface erodes. Ice sublimates, dust escapes, the crust darkens unevenly. You get a patchy, heterogeneous surface, some areas bright, some dark, distributed randomly. 3I Atlas shows boundaries, sharp transitions between dark and bright material. The spectral change happens over distances of just a few meters. That's engineered precision. Finding 3, the mass is wrong. HERA's Doppler tracking allows mission controllers to measure how much the spacecraft's trajectory was perturbed by 3I Atlas's gravity. It's a tiny effect. The object is small, its mass is low, but HERA's navigation system is precise enough to detect shifts of millimeters per second. The result? Estimated mass, 6.2 1010 kilograms. For an object 500 meters in diameter, that translates to a density of 0.48 g-cm3. That's lower than previous estimates, which were around 0.6 g-cm3, and it's far lower than what you'd expect for solid ice, 0.9 g-cm3, or rock, 2.5 g-cm3. Even porous, comet nuclei, rubble piles held together loosely, rarely drop below 0.5 g-cm3. There are only two explanations for this density. A. The object is extremely porous, mostly empty space, with thin strands of material holding it together, like a cosmic sponge. B. The object is hollow. Option A is possible. Some comets are porous, but extreme porosity makes an object fragile. It should crumble under tidal stress, fragment during close solar approaches. 3I Atlas didn't fragment at perihelion. It held together. That argues against option A, which leaves option B, a hollow object, a shell surrounding empty space, exactly what you'd expect from a spacecraft, from a probe, from something built, because solid objects are inefficient. They're heavy. They require more fuel to accelerate, more energy to maneuver. If you're designing something to travel between stars, you make it as light as possible. You use thin walls, internal bracing, minimal mass. You make it hollow. The Hera data is transmitted to Earth on October 29th. By October 30th, it's been analyzed, cross-referenced, with the Hubble and JWST observations integrated into the growing profile. And the profile is becoming undeniable. Let me summarize where we are. Observed anomalies, confirmed by multiple instruments, jet-oriented toward the Sun, violation of radiation pressure, 4-hour pulse, now 3:58 medius, mechanical timing, nickel-rich, iron-poor chemistry, non-stellar ratios, PAHs without thermal history, fuel residue or high-energy processing, CO2-dominant outgassing, backward from typical comets, geometric shape with facets, non-natural weathering, banded thermal signature, organized surface features, thermal regulation at perihelion, active management, not passive heating. Pulsing hotspots aligned at 120-degree intervals, symmetric vents, layered surface composition, coating over substrate, low density consistent with hollow interior, spacecraft architecture, non-gravitational acceleration misaligned with visible jet, hidden propulsion, uniform deuterium ratio, homogeneous reservoir, not chaotic ice, molecular nitrogen presence, volatile preservation, unusual for comets, stable rotation axis despite outgassing, torque compensation, 15 anomalies, 0 natural explanations that account for all of them. At this point, the scientific community is fragmenting into camps. Camp 1, natural but unprecedented. Yes, it's weird. Yes, it violates models. But nature is full of surprises. We just haven't seen this type of comet before. Give it time, the data will make sense eventually. Camp 2, artificial but ancient. This is a probe, sent millions of years ago, autonomous, derelict, still functioning minimally, no longer communicating with its origin, just drifting, doing what it was programmed to do. Camp 3, artificial and active. This isn't a relic, it's operational. It's observing us. It might be transmitting data. It might be part of a network. We need to take this seriously. Camp 4, inconclusive. Suspend judgment. We don't have enough data. The anomalies are real, but extraordinary claims require extraordinary proof. We need more observations, more missions, direct contact. Which camp is right? Honestly, I don't know. But I do know this. We're past the point of dismissal. You can't look at 15 confirmed anomalies and call it coincidence. You can't look at thermal regulation, geometric vents, and hollow architecture and pretend it's natural. At some point, skepticism becomes denial. End of chapter 15, November 1st, 2025. 3I Atlas is now 2.5 AU from the Sun, beyond the orbit of Mars, fading fast. In 2 weeks, it will be too faint for even JWST to track. In a month it will be gone, a speck of light disappearing into the interstellar dark, and we'll be left with questions. When silence becomes unbearable, November 3rd, 2025. After 2 weeks of debate, a decision has been made, not by governments, not by the UN, not by any centralized authority, but by a coalition of scientists, engineers, and radio astronomers who decided, if we don't act now, we lose the chance forever. On November 5th, at 18 South UTC, the Parkes Radio Telescope in Australia will transmit a signal toward 3I Atlas. The signal is simple. Not a complex message, not an encyclopedia of human knowledge, not prime numbers or mathematical constants, just a pulse, a repeating pattern, on, off, at 1-second intervals for 60 seconds. Then silence, then 30 seconds. Later, another 60-second pulse. Repeat 5 times. Total transmission 6 minutes. Why this pattern? Because it's unambiguous. Natural radio sources, pulsars, magnetars, stellar flares, emit noise, static, occasional bursts. But they don't emit patterns. They don't pulse at precise 1-second intervals. If 3I Atlas has receivers, if it's listening, it will recognize this signal as artificial. And if it responds, even with a simple acknowledgement, a reflected pulse, anything, we'll know. The frequency chosen, 1420 MHz, That's the hydrogen line, the frequency at which neutral hydrogen emits radio waves. It's one of the most common frequencies in the universe, one that any radio-capable civilization would recognize. It's also relatively quiet. Minimal interference from Earth-based transmissions, minimal atmospheric absorption. If 3i Atlas is listening, 1420 MHz is where it would listen. The power output, 500 kilowatts. That's enough to send a detectable signal across interplanetary distances. At 2.5 AU, the signal will arrive at 3i Atlas with enough strength that even a small receiver, something the size of a car antenna, could pick it up. If the probe has any kind of radio capability, it will hear us. The decision wasn't unanimous. Some researchers opposed the transmission, citing the dark forest hypothesis, the risk of hostile response, the unpredictability of engaging with unknown intelligence. Others argued that the risk is overblown, that if 3i Atlas were hostile, it would have acted already. That silence achieves nothing, that this might be humanity's only chance to make contact with something beyond Earth. In the end, the pro-transmission camp won, not because they had better arguments, but because they had access. Parkes is a publicly funded observatory. The researchers operating it have discretion over observation schedules. They scheduled the transmission. And now, in 2 days, it happens. Here's what we're hoping for. Best case, 3i Atlas responds. A radio pulse, a modulated signal, a change in trajectory, anything that indicates it received the message and reacted. Neutral case, no response. The signal reaches the object, but nothing happens. Either the probe lacks receivers, or it's ignoring us, or it's incapable of responding. Worst case, the transmission triggers something unexpected. The probe accelerates away, or worse, it accelerates toward us. The signal travel time one way, approximately 20 minutes, 2.5 AU at the speed of light. If the probe responds immediately, we detect it within 40 minutes of transmission. If it takes time to process, to decide, to act, we might wait hours or days, or we might never hear anything at all. There's a phrase that keeps circulating through the research groups. Before belief, doubt intelligently. It's a reminder, a mantra, a way to stay grounded. We're not assuming 3i Atlas is artificial. We're testing the hypothesis. If it responds, that's evidence, strong evidence, maybe even proof. If it doesn't respond, that's also data. It tells us either it's not artificial, or it's not interested, or it's not capable. Either way, we learn something. But here's the uncomfortable truth. I want it to respond. I want to know. I want confirmation. I want the uncertainty to end. Because living with ambiguity is exhausting. It's maddening. Is this a comet? Is it a probe? Are we alone? Are we being watched? The questions gnaw at you. They keep you awake. They turn every new data point into a battlefield of interpretation. So yes, I want the signal to work. I want 3i Atlas to wake up, to notice us, to do something, even if that something is terrifying. Because terror is better than not knowing. End of chapter 16. November 5th is 2 days away. The transmission is scheduled. The telescopes are ready. The world, those who are paying attention, is holding its breath. And 3i Atlas keeps moving. Silent, indifferent, or maybe just waiting. When the universe doesn't answer November 5th, 2025. 18:00 UTC. The Parkes Radio Telescope, a 64-metre dish in rural New South Wales, Australia, rotates to aim at a specific point in the sky. Not at a star, not at a galaxy, at empty space, or rather, at the coordinates where 3i Atlas is predicted to be, given its known trajectory and velocity. At 18 Gasons exactly, the transmitter activates. A focused radio beam, 1420 MHz, 500 kilowatts, modulated in a 1-second on-off pulse pattern. 60 seconds of transmission. Silence. 30 seconds later, another 60-second burst. Repeat 5 times. 6 minutes total. And then, waiting. The signal travels at the speed of light, 300,000 kilometers per second. At 2.5 AU, 375 million kilometers, it takes 20 minutes and 50 seconds to reach 3i Atlas. If the probe responds immediately, The return signal would arrive at Earth at 1841:40 UTC. Parkes stays locked on target. Receivers active. Data streaming in real time. Dozens of astronomers are watching, either on-site or remotely, monitoring the signal spectrum for anything unusual. 1841 to 40, UTC, nothing. No pulse, no modulation, no spike in the 1420 MHz band, just noise, background hiss, the faint static of the universe. 1845 UTC, still nothing. Maybe the probe needs time to process. Maybe it's analyzing the signal, deciding whether to respond. They keep listening. 19 UTC, silence. 22 UTC, silence. By 22:00 UTC, 4 hours after the transmission, the team at Parkes makes the call. No response detected. Does that mean 3I Atlas isn't artificial? No, it means it didn't respond, or couldn't, or chose not to. There are a dozen reasons why a probe might stay silent. Its receivers are damaged. It operates on a different frequency. It's programmed to observe passively, not engage. It recognized the signal as primitive and irrelevant. It's conserving power. It's waiting for a different kind of message. It's a relic, barely functional, incapable of complex responses. Or, simplest explanation, it's not artificial at all. It's just a comet. A very strange comet. The lack of response doesn't disprove the hypothesis, but it doesn't help either. Within hours, the result is public. News outlets pick it up. Science blogs dissect it. Social media erupts. We sent a message to an alien probe. It ignored us. Scientists waste resources on interstellar prank call. 3I Atlas. Natural comet or just shy? The tone is mocking, dismissive, because the narrative has shifted. When the object was mysterious, when the anomalies were piling up, people were intrigued. But now that we tried something and it failed, the story becomes scientists overreacted. It's easier to believe we were wrong than to sit with uncertainty. But here's the thing. The anomalies are still there. The jet toward the sun, the 4-hour pulse, the thermal regulation, the hollow interior. None of that has changed. The object is still strange, still unexplained. The only thing that changed is we asked it a question and it didn't answer. There's a cognitive bias called normalcy bias. It's the tendency to interpret ambiguous information as confirming what we already believe. If you think 3I Atlas is natural, the lack of response confirms it. See? It's just a comet. Stop being paranoid. If you think it's artificial, the lack of response also confirms it. Of course it didn't respond. It's not designed to communicate with primitives. Both interpretations fit the data. Neither is proven. So, where does that leave us? With the same 15 anomalies, the same unanswered questions, the same unsettling sense that we're missing something. And with one additional data point, we tried to talk. It didn't talk back. Some researchers are relieved. Good. It's not hostile. It's not reacting. We're safe. Others are frustrated. We had one chance. We wasted it on a simple pulse. We should have sent something more complex, more meaningful. Still others are resigned. It was always a long shot. We did what we could. I'm in the frustrated camp. Because I think we asked the wrong question. We sent a pulse, a binary signal, on-off, the simplest possible pattern. But what if 3I Atlas doesn't recognize that as communication? What if it's looking for something more sophisticated? Mathematical constants, prime numbers, a visual signal, not audio. Or what if it's not listening at all? What if it's watching, using optical sensors, infrared cameras, gravitational detectors, and radio is just irrelevant to it? We assumed it would hear us. But maybe it's deaf. There's another possibility. What if it did respond, but not in a way we can detect? What if it sent a reply on a frequency we weren't monitoring, or in a modulation scheme we don't recognize? Radio telescopes are tuned to specific bands. If the response came at 10 GHz or 100 GHz or in the optical spectrum, we'd miss it. We were listening at 1420 MHz. Maybe that was the wrong channel. The frustrating part is, we'll never know. 3I Atlas is fading. It's 2.8 AU away now, moving. At 35 kilometers s, getting dimmer every day. In a week, even JWST will struggle to track it. In 2 weeks, it will be too faint for spectroscopy. By mid-November, it will be gone. We had one window, one chance, and it's closing. End of chapter 17. The transmission happened, the silence followed, and now we're left with exactly what we started with, questions without answers. But that's okay. That's science. You don't always get resolution. You don't always get the neat ending where everything makes sense. Sometimes you just get data and ambiguity, and the nagging suspicion that the truth is just out of reach. When one probe implies many, let's think bigger. If 3i Atlas is artificial, if it's a probe sent by an extraterrestrial civilization, then it's almost certainly not alone. Why? Because sending a single probe to explore the galaxy makes no sense. The galaxy is vast, 200 to 400 billion stars, hundreds of billions of planets, and space between them is empty, voids measured in light years, distances so large that even traveling at a significant fraction of light speed, a journey between stars takes thousands of years. No civilization sends one probe and hopes it finds something interesting. You send millions. This is the logic behind the von Neumann probe concept. A von Neumann probe is a self-replicating machine. It travels to a star system, mines resources from asteroids or moons, builds copies of itself, and sends those copies to other star systems. Exponential growth. Start. With one probe. It makes two. Those two make four. Four makes eight. Within a few million years, a blink of an eye on cosmic timescales, the entire galaxy is saturated. Every star system visited, every planet scanned, every potential civilization observed. It's the most efficient way to explore the galaxy, and if any civilization in galactic history developed this technology, even once, the probes should still be out there. So the question isn't, is 3i Atlas a probe? The question is, how many probes are there? And the follow-up, are we being watched by an entire network? Let's do some math. The Milky Way is roughly 100,000 light-years in diameter, contains 250 billion stars. Average distance between stars, 5 light-years. If a probe travels at 10% the speed of light, a reasonable assumption for advanced propulsion, it takes 50 years to travel between stars. If it spends 100 years in each system, mining, replicating, gathering data, the total time per hop is 150 years. Starting. From one star, how long would it take to reach every star in the galaxy? With exponential replication, the answer is shockingly short, less than 10 million years. That's faster than biological evolution, faster than the rise and fall of most species, faster than continents drift across Earth's surface. Now consider, the galaxy is 13.6 billion years old. If any civilization developed self-replicating probes at any point in galactic history, even billions of years ago, the probes should have reached everywhere by now, including us. This leads to a troubling question. Where are they? If the galaxy is saturated with probes, why don't we see them? Why haven't we detected a network of transmissions between probes? Why haven't we found ancient artifacts in our own solar system? On the Moon, on Mars, in the asteroid belt? Why are we alone? Several answers have been proposed. 1. The probes are covert. They're designed to observe without interfering. They hide, they blend in, they masquerade as natural objects, asteroids, comets, space debris, so civilizations don't notice them. 3i Atlas might be one of these. A probe designed to look like a comet, so we'd dismiss it. 2. The probes are rare, not saturating. Maybe the von Neumann model is wrong. Maybe civilizations send probes, but not self-replicating ones. Maybe they send a few thousand or a few million, and most of them miss interesting targets. We happened to intercept one. Pure luck. 3. The probes are dormant. They don't activate. Unless they detect something worth investigating. Most of the time they drift silently, conserving power. 3i Atlas might have activated because it detected us, our radio emissions, our atmospheric chemistry, something that marked us as technological. 4. The probes are ancient and decaying. They were launched billions of years ago. Most have failed. Only a few still function, barely, carrying out their missions on autopilot. 3i Atlas might be a ghost, still moving, still venting gas, but no longer. Transmitting, no longer fully operational. 5. There are no probes. We're alone. The simplest explanation: no civilization has ever built interstellar probes because interstellar travel is too hard, too expensive, or too pointless. We're seeing 3I Atlas as artificial because we want to see it that way. Confirmation bias. Which explanation is correct, I don't know, but I do think option 5, we're alone, is looking less plausible every day, because 3I Atlas isn't the only anomaly. Let's talk about Oumuamua again. When it passed through our solar system in 2017, it exhibited strange behavior: non-gravitational acceleration, movement not explained by gravity alone, unusual shape, elongated, tumbling, aspect ratio 10.1, no visible outgassing, no tail, no coma despite acceleration, high albedo, shiny surface, more reflective than typical asteroids. Astronomers proposed it was a comet, venting gas too faint to see. But the numbers didn't quite work. The acceleration was too strong, the outgassing too asymmetric. Some researchers, most notably Dr. Avi Loeb, suggested it might be artificial, a light sail maybe, a piece of debris from an alien spacecraft. The scientific community largely rejected that hypothesis, not because the evidence was bad, but because the claim was extraordinary. And extraordinary claims require extraordinary proof. But now we have 3I Atlas, another interstellar object, another set of anomalies: jet toward the sun, hollow interior, thermal regulation. Geometric structure: 2 objects, 2 sets of unexplained behaviors. At what point do we stop calling them flukes and start calling them a pattern? Here's a thought experiment. If 2 interstellar objects, out of 3 detected, show signs of artificial design, what does that tell us about the baseline rate? Let's assume we've detected every interstellar object that passed within 2 AU of the Sun in the last decade. That's probably true. Our detection systems are good. We found 3. Oumuamua, 2017, anomalous, possibly artificial. 2I Borisov, 2019, normal comet, clearly natural. 3I Atlas, 2025, anomalous, possibly artificial. That's a 67% anomaly rate. Now, interstellar objects are rare. We estimate 1 passes through the inner solar system every few years. Most go undetected because they're too faint, too fast, or poorly positioned. But if the anomaly rate is truly 67%, that implies most interstellar objects are artificial. That sounds absurd. But let's think about it. If the galaxy is filled with von Neumann probes, if millions or billions of them are drifting between stars, surveying planetary systems, then of course most interstellar visitors would be artificial. Natural interstellar objects, comets ejected from other star systems, are rare. They require specific conditions: a planetary system, gravitational interactions, high ejection velocities. But artificial probes, you can make as many as you want, launch them in every direction, saturate the galaxy. If probes outnumber natural objects 10 to 1 or 100 to 1, then detecting mostly probes is exactly what we'd expect. I'm not saying this is what's happening, I'm saying the data allows for it. And if it's true, then we're not just being visited, we're being surveyed, monitored, catalogued, evaluated by a network that's older than our species, older than our civilization, perhaps older than life on Earth. End of chapter 18. The network hypothesis is speculative, unproven, built on inference and extrapolation, but it's testable. If interstellar probes are common, we'll find more. In 5 years, 10 years, 20, we'll keep watching the sky, keep tracking fast movers, keep cataloging anomalies, and maybe one day we'll find one that talks back. When discovery changes everything. Let's step back for a moment. Forget the chemistry, forget the orbital mechanics, forget the spectroscopy. Let's talk about what it means if 3I Atlas is artificial. Because if it is, if we've just observed an extraterrestrial probe passing through our solar system, then everything changes. Not immediately, not practically, but philosophically. For most of human history, we believed we were central. The Earth was the center of the universe. The stars were lights on a celestial sphere. Humanity was special, chosen, unique. Then Copernicus showed us we orbit the sun. Galileo showed us the sun is one star among billions. Hubble showed us the universe is vast beyond comprehension. Every discovery pushed us farther from the center. We're not special, we're not central. We're a minor species on a minor planet orbiting a minor star in a minor galaxy, but we clung to one last piece of centrality. We're alone. Maybe not unique, maybe life exists elsewhere, but isolated. No contact, no communication, no proof. The universe is vast, but empty. If 3I Atlas is artificial, that last assumption collapses. We're not alone. We never were. And that realization, we are not alone, rewrites everything. Not our physics, not our chemistry, but our context. Suddenly, we're not the only intelligence in the galaxy. We're not the only ones looking up at the stars and wondering. We're part of a community, a galaxy full of civilizations, some active, some extinct, some still emerging. We're newcomers, late arrivals to a party that's been going on for billions of years. That's humbling, but it's also terrifying, because if the galaxy is full of civilizations and we've never heard from them, that means one of two things. A, they're hiding, deliberately staying quiet, avoiding contact. B, they're gone. They don't last. Civilizations rise, flourish, and collapse. And we're next. There's a concept called the Great Filter. It's the idea that something, some evolutionary step, some technological challenge, some existential risk, prevents most civilizations from becoming spacefaring and long-lived. Maybe the filter is behind us. Maybe it's the origin of life, or the evolution of intelligence, or the development of technology. Maybe we've already passed it and we're safe, or maybe the filter is ahead of us. Maybe it's nuclear war, climate collapse, artificial intelligence, bioweapons, something that wipes out civilizations before they can spread beyond their home planet. If the galaxy is full of probes but empty of living civilizations, that's evidence the filter is ahead, and we're walking toward it. I don't want to be alarmist, but I also don't want to be naive. If 3I Atlas is a probe, and if it's part of a network, and if that network no longer has anyone operating it, if it's just ancient machines, still running, still exploring, because that's what they were programmed to do, then we're looking at a graveyard, a galaxy that once had life, intelligence, civilizations, and now has only echoes. Alternatively, maybe the civilizations are still out there, thriving, expanding, watching, and they've chosen not to interfere. Maybe we're in a zoo, a nature preserve, a protected zone where younger civilizations are allowed to develop without contact. Maybe there are rules, laws, galactic protocols that say, do not make contact until the species is ready. And maybe we're not ready. There's a scenario called the Berserker hypothesis. It goes like this. Civilizations inevitably destroy themselves, but before they die, they send out weapons, autonomous, self-replicating machines programmed to find and destroy any other emerging intelligence. Why? Out of spite, out of fear, out of the logic that says, if we can't survive, no one should. If von Neumann probes exist, berserkers could too. And if 3I Atlas is one of them, if it's not an observer but a cleaner sent to eliminate competition, then we've just announced our presence to something hostile. I don't think that's likely. If 3I Atlas were a weapon, it would have acted by now. It had months to observe us, to target us, to strike. It didn't. It's leaving. But the fact that we can't rule it out is unsettling. Because we don't. No, we can't know. Not until we make contact, not until we understand intent. And by then, it might be too late. Here's the philosophical weight. If we're not alone, then every decision we make, as a species, matters more than we thought. Because we're not just deciding for ourselves anymore, we're deciding how humanity presents itself to the galaxy. Are we peaceful, aggressive, curious, fearful? Are we ready to join the galactic community, or are we still children, fumbling in the dark? And if we're not ready, if we're too divided, too warlike, too short-sighted, then maybe the galaxy is better off without us. Maybe that's why 3I Atlas stayed silent. Not because it couldn't respond, but because we're not worth responding to. End of chapter 19. These are heavy thoughts, I know, but they're worth thinking. Because 3I Atlas, whether artificial or natural, has forced us to confront something we've avoided for centuries. We might not be alone, and if we're not, we need to decide who we want to be. When the object fades into the dark November 10, 2025, 3I Atlas is now 3.2 AU from the Sun, beyond the orbit of Mars, fading rapidly. Its brightness has dropped below magnitude 23, too faint for ground-based telescopes, too faint for Hubble's continuous tracking. Only JWST can still see it. Barely. And even JWST is struggling. On November 10th, JWST executes its final observation of 3I Atlas. Not a long integration, just a brief snapshot. 30 minutes of infrared imaging at 5 and 10 micrometers, capturing what might be the last clear view humanity ever gets of this object. The image arrives at the Space Telescope Science Institute on November 11th. And it shows something unexpected. The thermal signature has changed. Throughout October, the object showed multiple hotspots, 3 distinct zones pulsing in sync with the 4-hour cycle. Now, in early November, those hotspots are gone. The object's thermal emission is uniform, smooth, passive. It's cooling. Here's what that means. For weeks, 3I Atlas was active, venting gas, generating heat, maintaining thermal regulation. Now it's inactive. The systems, whatever they were, have shut down. It's as if the probe, assuming it's a probe, has entered hibernation. Standby mode, power conservation, or maybe it's just done. Mission complete. The 4-hour pulse? Gone. The jet toward the Sun? Dissipated. The non-gravitational acceleration? Minimal within the margin of measurement error. 3I Atlas is now behaving like a normal object. Coasting. Passive. Dead. Does that mean it was never artificial? Or does it mean it's finished with us? There's a concept in engineering called graceful degradation. When a system fails, it doesn't collapse catastrophically. It shuts down non-essential functions, conserves remaining power, and enters a minimal operational state. Spacecraft do this. When solar panels degrade, when batteries fail, the onboard computer prioritizes survival over science. It stops transmitting. It stops maneuvering. It just